So hello guys, once again I welcome here all of you in this marathon session of highway engineering. Today we're gonna start our new chapter, which is pavement design. Okay, once again guys, I recall you that these session is only cover in this session we only cover only numeric portion. Okay, because a lot of question in gate examination from numeric portion. So yeah, let's start our pavement design. What it is? Pavement design. Okay, so from pavement design, first thing first is design factor, where we discuss maximum wheel load in design factors. We'll discuss maximum wheel wheel load. Okay, look guys, with maximum legal axle load is 8170 kg, and maximum equivalent single wheel load is 4085 kg. Okay, which these two is specified by IRC. So what that maximum legal axle load is 8170 kg, and maximum equivalent single wheel load, or in bracket you also let ESWL, is equal to or is 4085 kg. 4085 kg. Okay, these two is these two specified by IRC. Okay, so let's move forward to vertical stress under uniformly distributed circular load. Let's discuss vertical stress under uniformly distributed distributed circular uh, load based on Bosnick's theory. Based on, I'm sorry, based on Bosnick's theory. Bosnick's theory. So we have a formula for this. Vertical stress denoted by Z is equal to P 1 minus Z cube upon A square plus Z square 3 by 2. Here P is surface pressure and we further write P is P by pi A square, where A is radius of loaded area. Okay, so this is a vertical stress of uniformly distributed circular load based on Bosnick's theory. Guys, if you covered your soil mechanics, there is a chapter there, stress distribution in soil. There we also or there also we discuss this theory, vertical stress under uniformly distributed circular load on based on Bosnick's theory. Basically there are two theory, basic Bosnick's and Webster. So we'll discuss it later on soil mechanics, on marathon session of soil mechanics. Let's move forward for right now. Let's move forward to our next topic, which is there's one concept that When tire pressure when when tire pressure sorry wait a second. Yeah, when tire pressure is less than 7 kg per centimeter square, then then contact pressure is greater than tire pressure. Otherwise, vice versa. That is, when tire pressure is greater than 7 kg per centimeter square, then contact pressure is less than tire pressure. Okay, is less than tire pressure. So yeah, basically is equal to contact pressure is equal to load on wheel upon contact area. Contact area means, look that let's see, this is a road and there it is your wheel. So this is our contact area. This okay. Yeah, in this we have one table which will help you on to solve numericals. There will be one numerical from this. So let's see a table between contact pressure and tire pressure and rigidity factor. So let's say contact pressure here tire pressure, here rigidity factor. So let's say contact pressure is 7 kg per centimeter square, and let's say here 7 greater than 7 kg per centimeter square, and here less than 7 kg per centimeter square. Okay, so tire pressure here 7 kg per centimeter square and rigidity factor 1. Here tire pressure less than 7 kg per centimeter square and rigidity factor greater than 1. Here tire pressure greater than 7 kg per centimeter square and rigidity factor less than 1. Okay, so this is the one table between contact pressure, tire pressure and rigidity factor. So do remember this table. It will help you to solve numericals, okay, and gate examinations by taking assumptions. Okay, so do remember this table. So yeah, let's move forward to our next topic, which is equivalent single wheel load. What it is? Equivalent single wheel load. Equivalent single wheel load. Okay, it basically we denote it also as ESWL. Okay, yeah. So in ESWL, equivalent single wheel load, we have a spacing. We have a spacing is D plus 2A, where D is a clear, where D is clear gap between. Basically, it is a spacing between between the center of the wheels, and D is a clear gap between two wheel. Clear gap between two wheel, and A is radius. Okay, and S is spacing between the center of the wheels. Center of the, that means let's say this is surface, this is your wheel, so this is center of wheel and this is center of wheel, so this distance is you know s, and this is clear gap between is d. Okay, so center to spacing between center of wheel is spacing, and clear gap between wheel between two wheels is equal to d here, clear gap. Okay, so we have basically one formula for equivalent wheel load is log 10 ESWL is equal to log P to the base 10 plus 0.301 log, give me a second, yeah, 0.301 log P, log, sorry, log 2 by d by 2 to the base 10 upon log 2s by dt d by 2, 2s by d by 2 to the base 10. Basically we have formula, this formula of equivalent single wheel load, but here, but we'll discuss it from graphs for better understanding. Remember this formula, this will also help you, but before that let's say that represent here it is not 2, it is z. Okay, so here p is wheel load, and z is desired depth. Okay, so this is formula, do remember this formula. We'll understand this concept from graph. Let's say we have a graph like this. Okay, oh, wait a second, let's make graph in proper manner. Let's say, yeah, we have a graph something like this. Yeah, and here we have a value p, here we have a value p, and again here for p1, and here 2p. 2p. Okay, similarly here desired f z is equal to d by 2. This is for z is equal to d by, sorry, z is equal to d z1, this is z1, and here z is equal to 2s, s is spacing. Okay, so yeah, here we have p, here we have p1, p1, here we have 2p, here we have z is equal to d by 2, here we have z1, and here we have z is equal to 2s. Okay, give me a second, this is for this, join with respect of this. Yeah, So we have graph something like this. One more thing in this graph, we'll join this. Basically we need to join something like this. Now let's draw it by freehand, which will more clear if we draw freehand. So understand this. Yeah, let's say it is A, here it is B. From this graph we draw we draw we need to we need to modify a formula which will help you in numericals. That before that, let's see one concept here, that up to d by 2, up to stress d by 2, no stress overlap. Okay, up to d by 2 there's no stress overlap. So here ESWL, basically it is ESWL. Okay, and here is this Z log scale. Sorry, something like this. Yeah, so up to d by 2 there is no stress overlap, so ESWL is equal to P. And for depth of 2s, for depth of 2s, 2s or greater than 2s, ESWL is 2P. Okay, so let's try to modify a formula. Let's say log P1 to the base 10, this P1, this, minus log P to the base 10, this P, this P1 to the this P1, upon their respective depths, that is log Z1 to the base 10 minus log Z, that is d by 2 to the base 10, d by 2 to the base 10 is equal to, let's say here, log 2p to the base 10 minus log p to the base 10 upon their respective depths, that is log 2s to the base 10 minus log z, that is log d by 2 to the base 10. This is another formula on the basis of this graph. Do remember this for this formula, because it will help you on to solve numericals, because in numericals they'll give you this pressure or this depth. You'll need to make this graph, then solve by using this equation. Okay, so do remember both these formulas, this one, and from respect graph, this one. Okay, so let's move forward. Before that, there's a one concept that 80 kilonewton single axle considered to be single axle load. It's a kind of one important concept to kind of note, that 80 kilonewton single axle load, 80 kilonewton single axle is considered to be is considered to be single axle load, single axle load. Okay, let's move to our next topic, which is equivalent load factor. Basically there's only formula of this, which is equivalent load factor, or you'll say ELF. Okay, basically it is, we have formula for this, which is axle load divide by standard axle load, standard axle load whole power 4. So equivalent load factor have formula axle load divided by standard axle load of whole power 4. Okay, let's move to our next topic, which is failure criteria. Failure criteria. Yeah, in failure criteria, we have two things: fatigue criteria and rutting criteria. So let's discuss first fatigue criteria. Fatigue criteria, basically denoted as NF. Not, no, no, this is not denoted as. Basically, we have formula for this from NF is equal to 2.21 into NF. Basically is another thing, not fatigue criteria. Basically fatigue criteria is in under failure criteria. So for fatigue criteria we have a formula: NF is equal to 2.21 into 10 to power minus 4 into 1 of sorry, t power 3.89 into by, yeah, power 0.854. Okay, basically where here NF is, here NF is number of cumulative standard axle to produce 20% cracked surface area. That is, here NF is number of standard axle to produce standard axle to produce 20% cracked cracked surface area. Okay, and obviously you'll all know this is tensile strain at bottom. Remember, sorry, tensile strain at bottom. Okay, and obviously is elastic, you know, modulus of elasticity, so no need to write this. Okay, yeah, so this is all about the fatigue criteria. Let's move to rutting criteria, which is another part of failure criteria. That is rutting criteria. For this we also have, we have formula, which is 4 point here 4.165 into 10 to power minus 4 into by EV, uh, power 4.5337. Okay, obviously here again NF is number of cumulative standard axle to produce 20% cracked surface area, so that NF is the same, so no need to write this. And here one new thing, this is vertical subgrade strain at top. Okay, so this is all about the rutting criteria, and this is all about failure criteria, where we discuss fatigue criteria and rutting criteria. Do remember these two formulas. This is very important formulas. Okay, so let's move forward to our next topic, which is group index method. This is one of the good concept in pavement design. Basically there is a question, there will be chance a question from this topic from group index method in gate examination. Okay, so do remember, basically we have a one formula for this group index method. Okay, so we have formula for denoted as GI. It is denoted as GI. So we have formula for group index GI as 0.2a 0.2a plus 0.005 AC plus 0.00 sorry 0.01 BD Basically here A is percent is finer than 75 mu minus 35, and this whole, that is A, should not be greater than 40. Okay. Similarly, B is percent is finer than 75 mu minus 75 mu minus 15. This again, this also not greater than 40. And C is WL, liquid limit, minus 40, and should not be greater than 20. And D is IP, that is plasticity index, minus 10, should not be greater than 20. Okay. Basically, this WL and IP is a concept from soil mechanics. Okay. So if you'll study, we'll discuss it in soil mechanics portion. We'll discuss it later. Okay. So for right now, WL is liquid limit and IP is plasticity index. So yeah, this is group index. Let's move forward to our next topic, which is CBR method. Okay. Our next topic is, yeah, CBR method. CBR method. Basically here we have we have two concepts. That here we have thickness of subbase is equal to base is equal to total thickness minus thickness over subbase. Okay, is equal to total thickness minus thickness over subbase is over subbase. Okay, and thickness of base is equal to, and thickness of base is equal to thickness over subbase, thickness over subbase minus thickness over base, thickness over base. Okay, and thickness of pavement, we have a formula for thickness of pavement is thickness of pavement and represented as T in centimeter is under root 1.75 P upon CBR value in percentage minus P upon P pi. Okay, so this has formula for thickness of pavement represented as T in centimeter, that under root 1.75 P upon CBR percent minus P upon P pi. Okay, where P is wheel load, P is wheel load in kg, and P, small p, is tire pressure. Basically, this is a small p here, tire pressure in kg per centimeter square, in kg per centimeter square. Okay, so this is all about CBR method. We have thickness of pavement value. Now we'll move on to another part of CBR method, that is a modified CBR method. So let's move on to modif modified CBR method. Okay, so what it is? modified Cbr method. Yeah. So let's say we have ns is equal to 365. We have formula ns is equal to 365 1 plus r by 100 power n minus 1 into adf a into d into f upon r by 100. This is very important formula. There's a lot of question from this formula. Okay, so do remember this formula, where let's say what is what is these values adf and all of this. Let's where where a is number of commercial vehicle per day when pavement construction is complete. Okay, so a is number of number of commercial vehicle per day when pavement construction is complete. When pavement construction is complete. Okay, and r is rate of growth of traffic. R is rate of growth of traffic, and n is here, this n is design life. N is design life basically, which is about 10 to 20 years. 10 to 20 years. Okay, f is vdf. F is vehicle damage factor. Damage, give me a second. Vehicle, give me a second. Vehicle damage factor, known as vdf. Okay, and our d is lane distribution factor. Distribution factor, and our, yeah, our ns is, let's take another, give me a second so that I'll add pages here. Yeah, so our ns is number of cumulative and standard axle. Number of cumulative cumulative standard axle. Okay, basically we have a formula for a, for this a. We have formula that a is equal to p 1 plus r by 100 power x. Here p is number of vehicle per day at last count. Yes, p is number of vehicle per day at last count. Last count. Okay, and x is number of years between last count and completion of pavement construction. X is number of years between last count and completion of pavement construction. Completion of pavement construction. Okay, So yeah, so this is all about modified CBR method. Do remember these formulas, this one, this, and most important this formula. There's a lot of questions from there, from here. Okay, let's move on to another topic, which is vehicle damage factor. Another topic, this, which is vehicle damage factor. What it is? Vehicle damage factor, VDF. Okay, so basically we have values of VDF for, so for single axle load, for single axle load we have VDF is equal to axle load, axle load upon 8200, sorry, axle load upon 8200, 8200 power 4, power 4 is basically axle load in kg. Okay, and for tandem axle load, and for tandem axle load, axle load VDF is, for tandem axle load VDF is equal to axle load upon axle load in kg upon 14500 whole power 4. Okay, and do remember one concept related to vehicle damage factor, that in two way, if vehicle damage factor in one direction is higher than traffic of, then traffic of higher vehicle damage factor is considered. Okay, so remember this point, that in two way, if vehicle damage factor in one direction, is higher than, is higher than traffic of higher vehicle damage factor, then traffic of higher vehicle damage factor is considered. Okay, so yeah, remember this concept. Let's move to our next topic, that lane distribution factor, lane distribution factor, LDF. Okay, this is our denoted as lane distribution factor. So both vehicle damage factor and lane distribution factor we'll use here in this formula. Okay, so lane distribution factor, so yeah, look, for single lane, distribution factor is 1. For two lane single carriageway, two lane and single carriageway distribution factor is 0.5, and for four lane single carriageway, four lane and single carriageway our distribution factor is 0.40, 0.40, and for dual carriageway roads, for dual carriageway roads distribution factor is 0.75. Okay, So yeah, this is all about lane distribution factor. Let's move to our next topic, which is California resistant value method. What it is? California resistance value method. Okay, so we have formula for this. T is equal to K into Ti into 90 minus R upon C power 1 by 5. Okay, where T is total thickness in centimeter. Okay, and K is basically a constant, which have a value of 0.166, and our Ti is traffic index, and we have a value for traffic index is that Ti is equal to 1.35 into equivalent wheel load, that is EWL, average of equivalent wheel load, power 0.11. Okay, and this R is stabilometer resistant value. R is stabilometer resistance value. Okay, and obviously C is cohesiometer value. C is cohesiometer value. Okay, so do remember this formula. This is all about this formula. So yeah, we are for this we have a table here for this about this concept, which will help you to solve numericals. That table between number of axles and equivalent wheel load constants. So if you have a number of axle of, let's say, 2, 3, 4, 5 and 6, then you will get the EWL, that is equivalent wheel load constant, is for 2 330, for 3 1070, for 4 2460, for 5 4620, and for 6 3040. Okay, so do remember this table. It will help you to solve numericals. Okay, yeah, so this is all about California resistance value. One thing remaining in this, that is equivalent C value. So we'll discuss it here, that equivalent C value. Okay, basically we have formula for this, that T1 upon T2 is equal to C2 upon C1 to the power 1 by 5. Do remember this formula, because in somewhere in numericals there is, in last portion of the numericals, they will ask in that find equivalency value. So you'll find by using this formula. So okay, so for today this is it. So this is part one of pavement design. We'll discuss very soon for part two of pavement design. After that, we'll discuss previous year questions for part pavement design. So till then, practice a lot of questions of gate examination or any other examination you will target for. Till then, take care, and thank you so much for watching this video. Thank you.